a chapter on aromatic substitution reactions. So hopefully you all are feeling pretty good about that. If you go to OLS this upcoming week, that'll still be one of the topics that's covered. So if it's something that you need more practice with, please go to that. And we're going to move into something called organometallic chemistry. So organometallic chemistry is my subspecialty of organic chemistry. So I absolutely love teaching this particular topic in this class. It's my very favorite one to teach. I think it's quite a fascinating topic about the interaction that metals have with carbon and how we can utilize that. All right, let's get going. So learning objective 15A. So now we've moved into chapter 15. We skipped chapter 14 because you already covered it in 2301. That's the NMR spectroscopy chapter. So we jumped forward a chapter to chapter 15. And our first learning objective is to define what organometallic reagents are. And if you're reading along in the book, you can find this in sections 15.1 through 2. All right, so let's take a look at that word. Just like a lot of our descriptive words that we had previously in the last chapter, for example, nucleophilic aromatic substitution, meaning we have a nucleophile coming in and substituting an aromatic ring. This also has the definition sort of in the word there. So the definition of organometallic is a metal-carbon bond. So organo piece, of course, is going to tell us about the carbon. And then metallic is going to refer to the metal. So we're often going to just abbreviate metal as M. So organometallic is a metal-carbon bond. All right, so what can metal be? In this class, we're going to kind of look at some main group chemistry. So we're looking at the first and second columns in the periodic table. But organometallic chemistry sort of extends, and the type of research that I do it extends into what we call the D block of the periodic table. So all the way from the third to the 12th column in the periodic table. In my research lab, we work with the elements scandium, yttrium, titanium, zirconium, understanding exactly what those metals can do when they're bound to a carbon. We also drop down into the F block in the research realm as well, into the lanthanide. So we make complexes with metal carbon bonds, the lanthanum, gadolinium, dysprosium, holmium, all these elements that you've probably never heard their names pronounced. And then the other part of my research group, we work a lot with group 10 metals, nickel, palladium, and platinum. So organometallic chemistry is quite expansive, but we're going to really focus for the most part on magnesium, lithium, sodium, as well as later on, we're going to get into a little bit of copper chemistry. But it's quite a expansive set of reactions. All right, so we're going to look at some organometallic reagents. So I mentioned we're going to be dealing with some sodium and then acetylide. So we have a negative charge that's going to exist on our carbon there. Right, and in this case, we have those charges that are separated. We don't actually draw a bond between sodium and our carbon. So we would call this more of an ionic bond. Right, we learned about those in general chemistry. All right, in the case where we have a organometallic that has lithium, we do actually draw a bond to the methyl group or the carbon-based group. So this is methyl lithium. And because we draw that bond in, we consider this more covalent as a bond. All right, I said we also are going to deal with a lot of magnesium compounds. So magnesium bromide is going to be our counterion, and then we're going to bond that to a carbon-based group. So I've drawn an sp hybridized carbon, sp3, sp2. So you can sort of see that a lot of these different types of carbon can be used. So we would call this phenyl magnesium bromide. All right, just as a heads up, magnesium and manganese are not the same thing. Manganese is element number 25, magnesium is element number 12. I'll say these are probably two most commonly interchanged words that people get wrong. So I've drawn a bond there, so we can consider this as a covalent bond. So again, I don't really like the names of things because they're not very descriptive. I prefer calling this phenyl magnesium bromide, but in ALEX you might hear, or your book you might hear this referred to as a Grignard reagent. Right? It's not pronounced Grignard, it's Grignard. It's like French or something, I don't know. All right, so this brings in actually a sort of bonus learning objective for us. So learning objective 15B is to rationalize the reactivity of metal carbons bonds using electronegativity trends. Right, organic chemistry, we always care about the reactivity. We always care about how to rationalize it. So as always, we're going to take a look at our periodic trends when we rationalize this. All right, when we take a look at electronegativity, we have carbon, which is our star of this reaction, element number 6 in the periodic table. We know that carbon is more electronegative than an element all the way on the other side, like in the first column, for example, lithium, sodium, and magnesium. All right, so organometallic reagents, when we're thinking about this, the metal is less electronegative than carbon. All right, so when we're thinking about this metal carbon bond we have here, we can draw in our delta plus for electronegativity trends is going to be at the metal. The delta minus is going to be at our carbon. So that means that the carbon reacts as a carbanion, right? So carbon that's negatively charged. Right, and this is because it's more electronegative. We don't always think of carbon as a very electronegative element, right? We're always pointing out fluorine, oxygen, nitrogen, and chlorine as very electronegative. But when we're referring to electronegativity, we're always thinking about relative electronegativity. So things that are relative to another. So compared, carbon is less electronegative than like fluorine, for example. So that would affect how that reacts. But in this case, we're comparing carbon to something like lithium or magnesium. So they react as carbanions, or essentially negatively charged carbons. And so this means the reactivity of organometallics react as nucleophilic reagents and bases. So we're referring to the carbon portion that reacts as nucleophiles and bases. All right, and that's because we can rationalize that with our electronegativity. All right, so let's learn how to make these reagents. They're kind of funny looking. Sodium, lithium, magnesium. These are not reagents that we've used before or anything like them. So let's talk about the next learning objective is 15C. And that is the 2Ps, So remember, this means no mechanisms. So the two P's of the formation of organometallic reagents. And in the book, you can find this in section 15.3. All right, so how do we make these funny looking reagents? There's a couple of different ways that we can do it, all right? So we are going to we start out actually turning to electrophiles are gonna be our starting materials. Okay, so R in this case is gonna be a carbon that's sp hybridized or sp2 hybridized or sp3 hybridized, right? So we're really broadly reaching here. And our X is going to equal a halogen that's iodine, bromine, or chlorine. We've seen this before when we've left out certainly our radioactive halides and actinium, but we've left out fluoride in this series. So we don't make Grignard reagents or organolithium reagents or magnesium reagents from the fluorides. All right. So in order to make a lithium reagent, what we're going to do is we're going to add 2 equivalents of lithium. And what we end up with is a very nucleophilic reagent. So we end up with R bound to lithium. So R being our carbon group. And our byproduct of this reaction is going to be lithium with our halide. So just a salt. All right, so now we made something that acts as a nucleophile or a base, right? So this is why we need 2 equivalents of lithium, is we need to have some reason to get rid of our halide. So probably the most common reagent is N-butyl lithium. So N-butyl referring to the chain, and lithium. So that's probably one of the most common bases in all of organic chemistry. But we can have a more reactive base, and this is called T-butyl lithium. All right, and that's a super, super, super strong base. You have to be very, very, very careful with these reagents. We'll talk about that. All right, so that's for our lithium reagents. Now we're going to start with that same aryl halide. The same rules are going to apply. And when we're going to make organomagnesium reagents, turns out we actually only need 1 equivalent of magnesium. And our nucleophile base forms in this form. All right. So in this case, we just inserted magnesium in between the R and the X bond. All right, so we only need 1 equivalent of magnesium. And the reason is we're trying to balance our charges out. So lithium is in that first column of the periodic table. And we see that it would just have a 1+ charge, but magnesium would have a 2+ charge. So essentially what we've done here is we've just balanced our charges out, with R being a carbanion, so negative charge, and X being a negatively charged ion as well. All right, so we can have phenyl magnesium bromide is a super common one. Isopropyl magnesium chloride is another really common one. We can mix and match out our halogens and our R groups. I'll just draw the name out, isopropyl magnesium chloride. All right, the other one would just be phenyl magnesium bromide. That's how we form them. Those are our 2 Ps. All right, so we already know that these are going to react as nucleophiles and bases because, of course, we understand our periodic trends and the electronegativity of that. So let's go ahead and sort of take a look at what a reaction would look like with these acting as a base first. That's a little bit more simple. All right, so that's learning objective 15D. And this is a 4P reaction. So 4 P's of the formation of deprotonated species through organometallic reagents acting as bases. Spell that right. All right, and when we're thinking about this in the book, we could look it up in 15.4 is the chapter. All right, so we're going to deprotonate something. This is going to be a really, really, really excellent base. All right, so we're going to indicate we have methyl lithium, for example, as our base, but we could, of course, do this with our other organometallic reagents. And let's have something that is going to be an acid. So in this case, we're going to have methanol react as an acid. And then, of course, our learning objective tells us at the end of the day what we're going to get. What we're going to get is organometallic reagent acting as a base, which means it's taken a proton. And then we will have our lithium that's been acting as a counterion to our deprotonated species, which in this case, if we deprotonated methanol, we see is methoxide. All right, so we know what our base is, and now let's check out what our acid is. We often think of acid as, something that's really acidic, like HCl or hydrobromic acid or something like that. But anything can be an acid as long as you have a base that's stronger than it. So this is where our pKa values come in. And the pKa of this is approximately 17. The pKa of methyl lithium is approximately 45. So it's a really excellent base. So we'll talk about some of the ranges of pKas in just a moment. Okay, so what's going to be the fourth P for this? Well, we're going to take our electron density from our covalent methyl lithium bond. I'm going to go ahead and deprotonate that OH bond. And when we do that, we break the OH bond and we return those electrons back to our oxygen, which is why we have that methoxide that's negatively charged. All right, so this happens for other types of reagents. I'll just draw out an example of our phenyl magnesium bromide. For example, let's go ahead and deprotonate water. And if we wanted to form our product of that reaction, we would take our phenyl that's now deprotonated water, so it would have an H, ends up just as benzene. And we would have our magnesium bromide counterion along with our hydroxide anion. All right, the fourth P, of course, we take the arrow from the electron density between the magnesium and the bromide bond. We go ahead and draw that arrow to attack hydrogen, and we break that OH bond to get those electrons back. So this is what happens when we have Grignard reagents acting as a base. So I'm going to ask you a chime in question here that is going to get you thinking a little bit about this reaction. And we don't always talk about things like solvents, for example, but we are going to think through what types of solvents we can actually have for this. So if you go to the assignments tab and we go to chime in lecture 8, so what solvent can we have in this reaction based on what I just told you? So the question is giving you a couple of solvents that are pretty common in organic chemistry. We have water, something that's an ether or an ethereal solvent, or something that's an alcohol. What do you think? Based on what we just learned, what kind of solvent can we actually run these reactions in? As always, you're welcome to check with the person next to you and sort of see if your rationale makes sense. The reason why I'm asking this is that the University of Minnesota has a really great safety culture in chemistry, much better than most universities. And 2 out of these 3 solvents will make your reaction catch on fire. And 1 you'll be able to do the reaction in. Okay, let's see what people are thinking. All right, so we kind of have a mixed group of answers here. So when we're thinking through this, we know that if you were to add water to your reaction and you were to add alcohol to your reaction, when we're thinking about a reagent making a base, that sounds like a good idea. But if we're going to run a different type of reaction, like forming our Grignard reagent or using it as a nucleophile, and we were to add it into the alcohol base or the alcohol solvent or the water solvent, it turns out that it would just deprotonate those things, and then we wouldn't be able to do any other types of reactions. So it turns out actually you'll catch on fire if you use water or alcohol. All right, I'm not seeing any more people signing in. As always, if you have connectivity issues, please let me know at the end of the class. All right, I'm going to close that question. Okay, so that brings us to another learning objective that we have. Learning objective 15E, which is rationalize why organometallic reagents are incompatible with OH bonds. All right. So we just did this. We said that we need to run this reaction. If you wanted to make, for example, lithium methoxide and hydroxide, you certainly could do that through this method. But when we're doing other reactions that require an organometallic reagent, they react with these as solvents. So we need to make sure that we choose a solvent that's unreactive. All right. And this will make a little bit more sense when we study the other reactions. But this is just something I wanted you to start to think about now, is really compatibility of reagents. We're going to use we're going to learn about something called functional group protecting groups. And we'll find a way to get around some of these issues that we have. So we would use an ethereal solvent, ether-based solvent. Right, so oftentimes we use something called diethyl ether or something called THF, tetrahydrofuran. But you don't need to worry about the acronym. All right. So now let's put this into sort of a, put it together so that we can think about how we can actually use these. Check 1 second. Okay, so we're going to sort of combine the formation of organometallics and their function as a base. Right? How can organometallics be used to form other organometallics? So we use these as bases. At the end of the day, I don't think there's very many chemists that want to make lithium hydroxide or lithium methoxide. Instead, we want to use organometallics as bases so we could actually create a reagent that we might want to use. All right. So how would this work? Well, we would take this Grignard reagent or this organomagnesium reagent as our base. And then we would use it to deprotonate, for example, acetylide. We would use this hydrocarbon as an acid. All right, the pK of this is approximately 25. We rarely think of hydrocarbons as an acid, but it turns out you just need to have a better base. And in this case, what we can do is we can just deprotonate that. So we can form this methyl magnesium bromide is going to form methane. So it's going to deprotonate that acid. And then what it's going to do is you're going to be able to form your next organometallic reagent, which is this phenylacetylide that is now an organomagnesium reagent. All right, and we can do this. I told you the pKs matter a lot because we just need something that is more acidic. So the reason this is not going backwards, because the pK of methane is over 50. All right, so this is never going to go in the backward direction. We're never going to use a magnesium bromide acetylene reagent to deprotonate methane and go backwards because our pKs don't match. So in this case, what we've done is we formed a new organometallic reagent. Right, so sometimes based on the availability of what you have in the lab, you may not have some magnesium or lithium lying around to be able to form this reagent separately. You may need to use the base method. And this is just a really practical one. I would say, almost every single lab in Coltalk probably has a bottle of methyl magnesium bromide. And so they use this all the time as bases. And this only works because the pKs are favorable. So as I said, we always come back to acid-base chemistry, all right? We can't go in the other direction. All right. We can also use other bases. Alkynes are kind of hard to make our organometallic reagents with. So other bases work as well. So we can use sodium amide to make organometallic reagents, and we can use that same phenylacetylide that we have here. And in this case, we're just going to form ammonia, and that's going to form our base. The NH3 is ammonia. And then we would have our sodium cation. And then in this case, because we have sodium, you'll recall that it's our ionic bond. So this is sort of an addition to our learning objective before, which was how to form organometallic reagents. So this is learning objective 15C kind of coming back to us. All right, so alkyne organometallic reagents are often formed through deprotonation. This is certainly a little fact. As a student, I'd be like, oh, why do I have to learn this? Can't I just make them the other way? This is a reality. This is so much of the class content is informed by what researchers actually do in the lab, and this is what we actually do in the lab as we form these organometallic reagents, quite often from bases. All right. We'll get into a couple of examples in a moment, but let's go through our final learning objective, and then we'll sort of see how this works in reality as we put these molecules together. All right. So as I said, organometallics are, it's an entire field of research. So it's an incredibly powerful tool. So our final learning objective is 15F. And this is the 4 Ps of organometallic reagents acting as nucleophiles to make alcohols. So this is a 4P, so we're going to need the mechanism. So 4 Ps of organometallic reagents acting as nucleophiles. And specifically, we're going to make alcohols. And we're going to make them from carbonyls. So aldehydes and ketones, among other things, all right? And this is going to be, if you want to read about it in your book, 15.5. Okay, I think this is more exciting than acting as bases. We sort of make organometallic reagents to make other organometallic reagents so that they can do this. This is the thing that we care about. All right, so our nucleophile in this reaction is, of course, our organometallic reagent. So it does not just have to be our lithium reagent. It could be our magnesium or our sodium reagent. Doesn't really matter. So any organometallic. All right, so these are going to act as nucleophiles. So we need to figure out what our electrophile is. Our electrophile is going to be a carbonyl compound, as our learning objective says. All right, and at the end of the day, we're going to make an alcohol. But let's see first, let's follow our reaction arrows first to understand what our intermediate in this reaction is going to be. All right. Okay, so we're going to take our electron density from our metal carbon bond. And we're going to go ahead and we are going to attack our most electrophilic position with our nucleophile. Now, where's our most electrophilic position? You'll recall from the first day of class, carbonyl compounds have that delta positive charge at the base of that carbon and our delta negative charge on the oxygen. Because the oxygen is electronegative, pulling away electron density. So when we're thinking about the most electrophilic position, we're thinking about the carbon at the base of the oxygen. So we can go ahead and take our organometallic reagent. We start our arrow at our nucleophile. It's going to attack that most electrophilic position to make a carbon-carbon bond to that. We can't, of course, have 5 bonds to carbon. So we're going to need to release a bond from carbon by breaking that CO double bond and returning those electrons back to that electronegative oxygen. All right, so now we can see that we formed a new carbon-carbon bond. So let's go ahead and draw that in. So our R group is now bound to that carbon. And we have our oxygen that is negatively charged because we've returned electron density to it by breaking that CO double bond. Of course, we always need to carry through our counterions. So we have a lithium plus counterion. All right, so this is the first step of the reaction. So step 1. This is what you get at the beginning, all right? So our first arrow here is our nucleophile, our R minus. Attacks electrophilic carbonyl carbon. All right. Then our second arrow, number 2, is going to be our CO double bond breaks to give a CO single bond and electrons back to oxygen. Make it negatively charged. All right, so this is step one in the reaction. So sometimes in chemistry, we have a two-step reaction. So the reason why I had you do that chime in question, it may not have sort of necessarily made sense at the time, is because we need to consider this is not what we wanted, right? This is not an alcohol. We have no protons in this reaction. We couldn't run this in a solvent with any protons like methanol or water or something like that. But at the end of the day, we need to make an alcohol, right? That's what our learning objective says that we make at the end of the day. So we need to think about a way to find a proton source, right? So this is a two-step reaction, all right? So we need to do step two, all right? All right, and in this case, we need to add in acid or water. So I'll do this with H3O plus just to make it easy. All right. So we need something called a workup. Okay, so we have our lone pair on oxygen from that negative charge is simply going to deprotonate our acid, and that's going to generate our alcohol, and it's going to be water. Right, so that means the step three is our basic alkoxide deprotonates acid in a separate step. I'll say acid or water. So we would call this a workup step. All right, and the reason is, remember, if we're going to be using these reagents, they cannot be in a solvent that has any protons. They'll just act as a base and they'll never do your nucleophilic addition, all right? So that's why we have two steps in this reaction. This is something that unfortunately trips people up every year on the exam. That's why I'm taking the time to sort of slow down. So let's talk about what the two P's are for this. So we have step one. This is your organometallic reagent. And your electrophile. Step two is H3O plus or just any acid or water after the reaction is over. So every year we have people add everything all in one step. So over the arrow, when we ask on the exam for reagents and conditions, they add in their organometallic reagent, their electrophile, and H3O plus. That's going to make the reaction catch on fire, all right? And it's incompatible, and that was one of our learning objectives, to understand the incompatibility. So what you're going to do is you're going to write a 1 for step 1, and you're going to write a 2 for step 2. You're just going to separate them out, all right? All right, so let's take a look at what that would look like on an exam. If I asked you for the two P's of this reaction, okay? So let's go ahead and take a look at what this molecule is, and this is gonna be our practice molecule. Okay, so we are going to have the opportunity to think about how we would make this, right? So this is called retrosynthesis. meaning going backwards, like retro, backwards. So retrosynthesis, how would we get to this reaction? So when we're doing retrosynthesis, we're thinking to ourselves, what bonds can we make? All right. Well, let's take a look at our learning objective. It says we can use 4 Ps of organometallic reagents acting as nucleophiles to make alcohols from carbonyls. Well, this looks like an alcohol to me, so I think we could probably use this particular learning objective in order to make this molecule. So what we would know is we're going to make an alcohol. So we're going to go ahead and break this bond here. And we're going to turn that into, our learning objective said, an organometallic reagent. So let's just use methyl magnesium bromide, for example. And it said a carbonyl compound. So in this case, this looks like it's probably an aldehyde. All right, so that's what our learning objective told us. We can combine an organometallic with a carbonyl compound, an aldehyde or a ketone, to make what we want. So let's go ahead and see what this looks like in the forward direction. Well, one of our learning objectives said that we could use aryl or alkyl or alkyl halide. So let's try with methyl, phenyl bromide. And our reagents for this would be our magnesium 0. So just one equivalent of this. I don't think you really need the oxidation state, but okay, so great. We're going to make one of our reagents with the reaction that we just learned today from our learning objective, right? We added in our magnesium, one equivalent, and now we've made our organometallic reagent. Okay, great. Now the next learning objective said that that's how we can make our alcohol. So let's bring in our carbonyl compound. All right. All right. So this would be our step 1. I would draw a 1 there. Then in step 2, I would draw some acid, H3O+. I've designated those are 2 separate steps. And then when we do that, we will get to the final product that we're looking for. Right, because we've added in that H3O+, we protonated our alcohol. We are good to go. All right, so let's do another practice problem, all right? Okay, so let's make this compound here. It is going to be, as you probably guessed, another alcohol. And so what do we think is the retrosynthesis? What carbonyl compound plus what organometallic reagent are you going to use to make this molecule? So go ahead and think about that for a few seconds. Then maybe check with your neighbor, see what they say. This is not a quick trick question. Turns out there are 2 correct ways to make this molecule. All right, let's identify a potential alcohol, okay? Not a potential alcohol, a potential carbonyl compound. Okay, so let's say we broke our bond here. That means that we have divided our molecule up into 2 fragments, a 2-carbon fragment and a 2-carbon fragment with the alcohol on it, all right? So let's go ahead and see what we would make with our Grignard reagent or our organomagnesium reagent, organolithium reagent. So that's 2 carbons. Let's stick a lithium on it. You could have stuck a magnesium or sodium, doesn't matter to me. And now let's think about what our carbonyl compound would look like. 2 carbons in it with a carbonyl. Awesome. That's how we would make this molecule. Now, perhaps you thought about this differently and you said, I see an alcohol that can be broken on both sides. What if we broke this carbon-carbon bond? Right, that means our first fragment, our nucleophile, would be here on this methyl group. And then we would have a carbonyl compound from that 3-carbon fragment. So instead of constructing this from a 2-carbon fragment and two 2-carbon fragments, we could instead use methyl lithium for that yellow portion that I've highlighted. And then we could have our carbonyl compound have 3 carbons in it. Both of these are perfectly valid answers. All right. So what I want you to do at the end of the day, I'll write it out. But what I want you to do is I'm leaving this as a practice problem for you and your homework, okay? So for you, I'd like you to provide the reagents for the forward synthesis. And then after class, I'll write this in and post the notes so you have the answer. For both of them, just practice with both of them. How are you going to make that organometallic reagent, and how are you going to make that final compound? The 2 steps in the workup. All right, that's it.